This drastically reduces energy wasted during idle listening periods.
Smart listening.
Then, compressed data transmission. Sending smaller amounts of data inherently requires less transmission time and therefore less energy. Use efficient compression algorithms. Adaptive duty cycling is important too. Periodically switch communication components between active and low-power sleep states. The duty cycle, the percentage of time it's active, can be adjusted based on current needs, especially good for applications with bursty activity.
Cycling between on and off.
Right. Batch data transfers is another good one. Instead of sending small bits of data frequently, store the data locally on the device for a period, and then transmit it less frequently in larger batches. This reduces the overhead energy costs associated with establishing connections, handshakes, etc.
Send less often, but bigger chunks.
Precisely. Also, simply sending only important information. Filter out extraneous or redundant data before transmission. Don't send noise if you only care about the signal. And finally, a really important trend. Processing data locally, which ties into edge computing. Perform preliminary data processing, filtering, or aggregation directly on the embedded device itself. This reduces the sheer volume of raw data that needs to be transmitted wirelessly, which is often the biggest power hog.
Do the work locally, send less data.
Exactly. So the key insight here is really that it's not solely the choice of the communication protocol, but the overarching data handling strategy, when you send, what you send, how you send it, that profoundly influences communication energy consumption.
That's a great summary. Okay, this is amazing. All these sophisticated ways to save power, squeeze every last drop out of a battery. But what if? What if we could just make power from the environment itself? Tell us about energy harvesting. This sounds almost like science fiction.
It does have that feel sometimes, doesn't it? Energy harvesting is a truly transformative approach. The goal is to make embedded systems partially or even fully self-sustaining by capturing ambient energy from their surroundings. The main aim is to dramatically extend operational lifetime, potentially indefinitely, or at least facilitate on-site charging without manual intervention like changing batteries. The basic process usually involves 3 stages. Energy capture using some kind of transducer, energy conversion into usable electrical form, and then energy storage, typically in a small rechargeable battery or increasingly a supercapacitor.
Capture, convert, store. What are the main ways they're actually capturing this energy? What are the sources?
There are several promising techniques being used and researched. Probably the most common is solar energy harvesting. This uses small photovoltaic, or PV cells, essentially tiny solar panels to convert sunlight directly into electricity. Efficiency depends on the PV cell technology itself, typically 15–20% for common types, but also heavily on the amount of light available, irradiance, and the panel's orientation. You see this increasingly in wearables like smartwatches, outdoor environmental monitoring stations, smart agriculture sensors.
Solar makes sense. What else?
Vibration energy harvesting. This converts mechanical vibrations or movements into electricity. There are a couple of main methods. Piezoelectric conversion uses materials, often ceramics like PZT, that generate an electric charge when they're mechanically stressed or vibrated. Electromagnetic conversion uses relative motion between magnets and coils to induce a current, like a tiny electrical generator. Applications include powering sensors in industrial machinery for predictive maintenance, capturing machine vibrations, car tire pressure sensors, capturing road vibrations, even batteryless remote controls powered by the button click motion.
Harvesting vibrations. Clever.
Then there's thermal energy harvesting. This converts temperature differences into electricity using thermoelectric generators, or TEGs. These rely on the Seebeck effect, where a voltage is created across the junction of 2 dissimilar materials when there's a temperature gradient. Applications include capturing waste heat from engines, industrial processes, or even body heat for wearables, though the power levels from body heat are typically very low.
Using heat differences.
Okay, we also have RF, or wireless, or electromagnetic energy harvesting. This involves capturing and converting ambient radio frequency waves from sources like TV broadcasts, radio stations, Wi-Fi routers, cellular towers. The power levels available are generally very low, but potentially enough for ultra-low power devices, especially if the source is nearby. Often called rectennas, antennas coupled with rectifying circuits.
Harvesting radio waves. Wow.
Yeah, it's an active area. And one more niche one is pyroelectric energy harvesting. This is related to thermal, but it converts changes in temperature, fluctuations over time, into an electric charge, used in some specialized sensors.
Okay, solar, vibration, thermal, RF, pyroelectric. Lots of options. But it sounds like relying on the environment for power must have its challenges, right? It's not always sunny or vibrating.
Absolutely. That's the major challenge. The inherently intermittent and variable nature of many ambient energy sources. Solar depends on light, vibration depends on motion, RF depends on nearby transmitters. These sources often provide only very low levels of energy, and they're subject to frequent interruptions. This intermittency means you almost always need robust energy storage, rechargeable batteries or supercapacitors to buffer the energy and provide a stable power supply to the embedded system when the harvesting source isn't active.
So storage is key to smooth things out.
Critically important. This challenge is also driving innovation in so-called batteryless IoT devices. These are designed to operate purely opportunistically, performing computations or transmissions only when enough energy has been harvested and stored, often in a capacitor. They might wake up, do a quick task, and go back to sleep until recharged.
Batteryless, operating intermittently. Where are we seeing energy harvesting making a real impact today, or where do you see the biggest potential?
The impact is growing significantly. Wearable devices are really ideal candidates. Their power requirements are often low, and the prospect of self-sustaining power is incredibly appealing to users. Solar and kinetic vibration harvesting are particularly relevant here. We saw that example of a solar harvesting smart bracelet, the Bindi system. Its battery state of charge increased significantly even on cloudy winter days, and it showed potential for permanent operation with about 6 hours of daily direct sunlight.
Permanent operation from sunlight. That's the dream.
It is, and combining harvesting with other low-power techniques makes it more feasible. Remember the low-precision arithmetic in biomedical wearables, saving 54% energy. That makes the tiny amounts of harvested energy go much further. In industrial IoT, energy harvesting is huge for reducing maintenance costs and improving safety by eliminating battery replacements in hard-to-reach or hazardous locations. Vibration harvesting powering sensors on rotating machinery is a classic example. For environmental monitoring and smart agriculture, solar power is enabling sustainable long-term deployment of remote sensor stations for continuous data collection without needing power lines or frequent battery changes.
Makes sense for remote places.
Definitely. Now, there's still challenges, of course. Low energy density of sources, the intermittency, limits on conversion efficiency, and broader limitations like cost, scalability for mass production, and for wearables. Things like biocompatibility, washability, durability are all factors. But the vision of health bracelets operating for 20 years without charging, or even bioabsorbable pacemakers powered by internal body functions. That stems directly from advances in energy harvesting combined with ultra-low power design. It fundamentally alters the power paradigm for embedded systems, enables truly batteryless IoT devices, and has the potential to significantly reduce electronic waste from discarded batteries.
A fundamental shift. Okay, this whole area, from hardware tricks to software smarts to harvesting energy, it's clearly incredibly complex. What are the biggest trade-offs engineers constantly have to wrestle with? It sounds like you just can't optimize everything at once.
That's exactly right. Designing these ultra-low power systems is inherently complex, often what we call over-constrained. You're trying to satisfy many competing requirements simultaneously. Engineers must constantly balance multiple critical factors. The absolute core dilemma is power versus performance. Higher operating frequencies mean tasks complete faster, better performance. But as we know, power increases significantly with frequency and voltage. Pushing for ultra-low power often means compromising on raw speed. This balance isn't static, it's dynamic, adjusted by techniques like DVFS. But designers have to define clear priorities up front. Is minimum power the absolute goal, or is meeting a certain performance level non-negotiable? Then they implement adaptive strategies.
Power versus performance, the classic trade-off.
It really is. Then there's size versus performance. Miniaturization is a constant demand, especially for wearables and IoT. But shrinking the size can limit performance due to challenges with thermal management, getting heat out of a tiny space, power delivery networks, or simply the physical space available for components like larger processors or batteries. A smaller battery in a smartwatch directly limits the processing power you can sustainably use.
Size versus performance. Okay.
And related is size versus cost. Generally, smaller, more integrated devices require more advanced, specialized components and more complex manufacturing processes, which usually translates to higher costs.
Smaller often means more expensive.
Often, yes. Then there's power versus reliability. This is a subtle but critical one. Lowering supply voltage too aggressively to save power can actually increase the system's susceptibility to noise and transient faults, potentially reducing reliability. Limiting sensor scan times or communication retries to save power might reduce robustness against interference or temporary link failures, and inadequate power management leading to excessive heat generation will definitely reduce the lifespan of components.
Power versus reliability. Interesting angle.
And finally, just complexity itself. As systems become more sophisticated, integrating more features, sensors, communication modes, their inherent complexity increases. This often leads to higher baseline power requirements, more complex power management needs, more heat, and reduced battery life if not managed carefully. And paradoxically, many of the advanced low-power techniques we've discussed, DVFS, power gating, complex scheduling themselves, add significantly to the design complexity.
So the solutions add complexity too. It's a cycle.
They can be, yes. It requires very skilled design teams and sophisticated tools.
Okay. Beyond those core trade-offs, power, performance, size, cost, reliability, complexity, what about specific challenges in key areas like memory, communication, and maybe even security in these tiny, resource-constrained systems?
Good points. Yes, there are specific limitations to address. For memory, lightweight systems are obviously constrained by the amount of available RAM and flash. But, as we discussed, crucially, it's the number of accesses to that memory that's often the primary driver of energy consumption, not just the size itself. Inefficient memory access patterns in the software can completely negate the benefits of having low-power memory hardware.
Access patterns again.
Exactly. For communication challenges, both communication within the chip over internal buses and inter-device wireless communication are major sources of power consumption. This can be exacerbated in very tiny processors that might lack sophisticated bus management or DMA controllers. And as we noted, wireless communication often dominates the total power consumption budget for connected devices.
Wireless is the big hog.
Often, yes. And security limitations are a growing concern. Implementing robust security encryption, authentication, secure boot presents considerable difficulties in these resource-constrained systems. Traditional security mechanisms often involve complex computations, like public key cryptography, and extensive communication exchanges, both of which are very power-hungry. Despite these constraints, security is paramount, especially for devices handling sensitive data or operating in potentially hostile environments. Specific limits include a lack of large, secure storage for complex cryptographic keys, insufficient computational power for heavy algorithms in real time, low communication bandwidth limiting protocol overhead, and just limited battery power for energy-intensive security processes.
Security versus power, another tough trade-off.
A very tough one. And all these challenges, memory, communication, security, performance, power, they're deeply interconnected. You can't really solve one without impacting the others. It truly is a multi-objective optimization problem. It absolutely requires a holistic, co-design approach, considering hardware, software, and communication design together from the very beginning.
Holistic co-design. So how do designers even begin to tackle this incredibly complex puzzle? It sounds like you can't just guess or build prototypes until it works.
Guessing is definitely not an option. Not with today's complexity and time-to-market pressures. The key lies in the importance of accurate modeling and simulation. Estimating energy consumption accurately is incredibly complex. It depends on a multitude of dynamic factors. Different operating modes, varying workloads, which peripherals are active, communication patterns, even environmental factors like temperature. Simply selecting components labeled low power is insufficient without a clear understanding of how they interact within the complete system under real software loads.
You need to see the whole picture.
Precisely. The solution is leveraging advanced power-aware electronic design automation, or EDA, tools and sophisticated system-level simulation environments. These tools allow designers to build virtual prototypes of their system. They can load the actual firmware, the real software, onto these virtual platforms, and then run realistic usage scenarios, accurately simulating and evaluating power consumption long before any physical hardware exists.
Simulating with real software. That's powerful.
Extremely powerful. This enables those co-design approaches we talked about, integrating hardware and software development flows. It helps identify power bottlenecks early, simulating different architectural choices, different algorithms, different component selections early in the design phase allows for highly informed decisions. This drastically reduces development costs by catching problems before expensive hardware respins, and it significantly accelerates the time to market. This shift-left approach, moving analysis and verification earlier in the design cycle, it's really no longer a luxury for low-power design. It's a fundamental necessity.
Modeling and simulation are essential, not optional. Okay, as we look towards the future then, what are some of the cutting-edge innovations? What's on the horizon that's going to push low-power design even further?
There are several exciting trends and emerging technologies really pushing the boundaries. One big one is AI-driven power management, We touched on this, but the integration of artificial intelligence is increasing rapidly. Machine learning algorithms are being trained to learn complex power consumption patterns and workload trends within a system. This allows them to make highly accurate predictions about future needs and proactively adjust power states, voltage, frequency, maybe even task schedules for optimal efficiency. The goal is minimal energy consumption without compromising performance or user experience. We're already seeing this applied effectively in areas like smart building energy management for HVAC and lighting.
AI managing power dynamically.
Exactly. Another important area is the use of domain-specific architectures, DSAs, and 3D integrated circuits, ICs. DSAs are hardware configurations like specialized accelerators or FPGAs that are highly tailored for specific types of workloads. Think AI inferencing, cryptography, signal processing. By being specialized, they eliminate the overhead of general-purpose processors and can achieve superior energy efficiency for those specific tasks.
Hardware designed for one job really well.
Right. And 3D ICs involve stacking multiple silicon dies vertically within a single package. This allows for very short, high-bandwidth connections between the layers. Shorter wires mean lower parasitic capacitance and resistance, which directly translates to lower power consumption for communication within the chip. The main challenge here, though, is thermal management, getting the heat out from those middle layers.
Stacking chips vertically, cool but hot.
Potentially, yes. Needs careful thermal design.
What other big ideas are maybe changing the game at a more fundamental level? Less about architecture, more about computation itself or materials.
Good question. Two really interesting areas there: approximate computing and novel semiconductor materials. Approximate computing is fascinating. It fundamentally challenges the traditional computing paradigm that demands perfect, exact computational precision at all times. Instead, it intentionally introduces controlled, minimal inaccuracies into calculations or data storage to significantly reduce power consumption, while still ensuring the final result is good enough or acceptable for the target application.
Trading perfect accuracy for lower power.
Exactly. It's particularly beneficial for applications involving perceptual data, like image or audio processing, or tasks like neural network inference, where minor errors in intermediate calculations often have little or no perceptible impact on the final output quality. Remember that biomedical wearable example using 16-bit posits instead of 32-bit floats? That's a form of approximate computing. Saved 54% energy with acceptable results. This represents a real shift in design philosophy from striving for exactness at all costs to achieving sufficient correctness for optimal energy.
Sufficient correctness, I like that. And new materials.
Yes, novel semiconductor materials. There's ongoing research into materials beyond traditional silicon. Things like carbon nanotubes, CNTs, and gallium nitride, GaN, are being explored for building transistors and integrated circuits, potentially offering superior energy efficiency, higher speeds, and reduced leakage currents compared to silicon, especially for certain applications like power electronics or high-frequency devices. Graphene is another material with incredible electrical conductivity and mechanical properties, showing promise for applications in energy harvesting, flexible electronics, and advanced microelectronics. It's still mostly in research, but holds potential.
Carbon nanotubes, gallium nitride, graphene. Beyond silicon. Exciting stuff. Okay, this is all incredible in theory, these techniques and future trends, but where do we see these principles actually working today? In the real world, what kind of impact are they having? Maybe with some numbers.
Absolutely. The real-world impact is significant and measurable. Let's look at some case studies, starting with IoT devices. For battery life extension, we see low-power wide-area network technologies like NB-IoT combined with aggressive power optimization on the device, achieving operational lifespans of up to 10 years for certain IoT modules on a single battery. That's huge for remote deployments.
10 years.
It's achievable in the right low-data scenarios. Strategic use of sleep modes and duty cycling is critical. Systems using deep sleep modes with wake-on interrupt mechanisms have demonstrated up to 90% enhancement in battery life compared to always-on or less optimized approaches. Dynamic scaling techniques can reduce consumption by 70% or more during idle periods. We saw that sensor node example going from 15 milliamps active down to a mere 8 microamps in hibernation. That's an orders of magnitude difference.
Huge drop.
A smart thermostat case study showed up to 50% improvement in battery life by intelligently entering low-power modes when no user interaction or significant temperature change was detected. And in remote metering, accurate battery life prediction is key. One study using a sophisticated model achieved a mean absolute error of less than 4.1% and an R-squared value over 0.96 for predicting the battery state of charge, allowing for better maintenance planning. It's important to reiterate, though, these improvements aren't usually from one magic bullet. It's almost always a synergistic combination of hardware choices and clever software strategies working together.
Synergistic approach. What about the devices we wear every day? Wearable tech. How are they benefiting?
Wearables are another great showcase. We already mentioned low-precision arithmetic, that biomedical wearable study using 16-bit posits for cough and ECG detection resulted in 38% smaller hardware and up to 54% less energy consumption with no compromise in the actual detection performance. That's a huge win.
Half the energy, same result.
Pretty much. And the Solar Energy Harvesting Smart Bracelet, the Bindi system, showing battery SOC increase from 19% on cloudy winter days up to 53% on sunny spring days. That potential for permanent operation with just 6 hours of daily sunlight is game-changing for user convenience. Even things like gesture recognition on smartwatches. Studies have focused on creating energy-optimal applications that maximize the number of gestures recognized accurately while strictly adhering to predefined energy budget constraints. For wearables, performance isn't always about raw speed. It's often about meeting specific application-level metrics like recognizing a gesture quickly enough while absolutely minimizing energy draw. Approximate computing is a prime example of this tailored optimization.
Tailored optimization for wearables. And finally, what about heavy industry? Places where devices might run constantly, reliability is paramount, maybe harsh conditions. How is low-power design making a difference there?
Industrial systems present unique challenges, but also see significant benefits. In industrial wireless sensor networks, WSNs, for example, a gas monitoring WSN achieved high reliability and low power consumption by intelligently alternating between active sensing cycles and extended low-power sleep cycles. This design allows for scalable deployment of a large number of low-cost, small-size sensor nodes that can operate for years. We even saw an example of an automated pig weight monitoring system using 3D image recognition. Developed as an industrial prototype, it integrated complex functionalities, but within an energy-conscious framework suitable for agricultural environments.
Monitoring pig weight with low power.
Shows the breadth of application. More critically, think about battery management systems, BMS, for electric vehicles or hybrid electric vehicles. Advanced BMS designs leveraging low-power microcontrollers and sophisticated algorithms have achieved very high accuracy, like 96–98%, in estimating the battery's state of charge, SO, and state of health, SOH. This isn't just about saving a tiny bit of power in the BMS itself. It's crucial for ensuring safe operation, maximizing usable range, and significantly prolonging the expensive battery pack's overall lifespan.
BMS accuracy is key for EVs.
Absolutely. And looking broadly at IoT-driven innovations in Industry 5.0, one case study showed a 5.7% decrease in overall energy usage in an office environment simply by analyzing data from IoT sensors, monitoring occupancy, lighting, and HVAC usage, allowing for smarter control. So for industrial systems, low power isn't just about battery life. It's often about fundamentally improving overall operational robustness, minimizing costly maintenance interventions, and ensuring long-term dependability, sometimes over decades.
Robustness and dependability. And I think some sources quantified savings, like processors with multiple power states giving a 60% reduction in active power.
Yes, figures like that are common for well-implemented DVFS and power state management.
Regular firmware updates for power management adding up to 10% more savings.
That highlights the software role, yes. Continuous improvement is possible.
Adopting LoRaWAN or Zigbee giving around a 60% cut in transmission power needs.
Compared to less suitable protocols for low-data applications, absolutely.
And nodes with integrated power management units boosting energy utilization by 30%.
Right, having that dedicated PMU or PMIC making intelligent decisions provides significant gains over simpler power schemes. Those numbers give a good feel for the scale of improvements possible.
Okay, so wrapping this up, what does this all really mean? We've taken a real deep dive here into this incredible, intricate world of ultra-low power embedded systems.
I think the core message is that achieving optimal energy efficiency isn't simple. It's a sophisticated, multi-layered approach. It requires seamlessly integrating advanced techniques across hardware, software, and communication domains. It's truly interdisciplinary. We journeyed from the basics, understanding static versus dynamic power, then explored hardware techniques like DVFS and clock gating, the importance of component selection and efficient power supplies. Then we moved to software, looking at code optimization, PowerWare algorithms, intelligent OS scheduling, exploiting slack time. And finally, we covered communication, choosing the right low-power protocols, smart data handling strategies, and the really game-changing potential of energy harvesting.
And it's crystal clear that it's this constant, complex balancing act. Performance versus power, size versus cost, reliability, complexity. all managed through sophisticated modeling, simulation, and those co-design approaches that you said are now just fundamental necessities.
Exactly. Looking ahead, the future points toward continued integration of AI for even smarter predictive power management. We'll see more advanced architectures like DSAs and 3D ICs and novel materials pushing efficiency further. The adoption of approximate computing will likely grow, challenging our notions of required precision. And enhanced energy harvesting technologies hold that promise of truly batteryless, maintenance-free embedded devices becoming more common. And one area we touched on that will only grow in importance is that intersection of security and low power, how to provide robust security without breaking the energy bank. That's a critical ongoing challenge.
Ultimately, it really feels like this field is about constantly pushing the boundaries of what's possible with embedded systems, making them smarter, incredibly more efficient, and fundamentally more sustainable for the future.
It is. And maybe that leaves us with a final thought for you, the listener, to consider. As these tiny, powerful, and increasingly efficient systems that might soon power themselves almost indefinitely, become truly ubiquitous, woven into the fabric of our lives, what new ethical considerations, what new societal questions might arise from technology that seems to run forever on its own?
That's a fascinating question to ponder. Thanks for taking this deep dive with us today. We hope you feel incredibly well informed, maybe even a bit amazed, and ready to explore even more. Until next time, keep digging for those insights.